In this video, we're going to look at importing a bracket design from Fusion360 and then running a structural or stress analysis on it. When you first launch DiscoveryLive, you'll probably see a window similar to this with some examples you can look through. I'm just going to close this box because it already has a new document open behind it. First things first, there's a few different navigation things here that are similar to Fusion360 but slightly different. Zooming, for example, isn't the center mouse wheel. You actually have to hold down Control, the center mouse wheel, and then move the entire mouse up and down to do your zoom. If you just click the center mouse wheel and move it, it's not pan like it was before. Now it's orbit. If you want to get pan in DiscoveryLive, you hold down Shift, the center mouse wheel, and then move the entire mouse. So I often, you'll see during the video, get those things confused. So that's part of the reason why. So keep your non-dominant hand on the keyboard. I'm right-handed, so I have my left pinky on Control for zooming, and Shift is my ring finger for pan. The file that we created in DiscoveryLive, we're just going to go ahead and open that from the File menu. For my example here, I saved it to the desktop, so I found it there, .sat. If you don't see it in your list here, it might be because the default when you open a file is it's only looking for space claim files. Those are the type of files that ANSYS, which is part of DiscoveryLive, or which makes DiscoveryLive, uses for their CAD design. So make sure that you change the file types. It's looking for to all files, and then you should see your .sat file right there. Double clicking that and opening it, it is, yes, the exact same one that I had created in Fusion. The thing we're going to do is we're going to see when I put a force out on the end of this design and I hold these two mounting brackets fixed in space because they're drilled into the wall, where is this thing going to have the greatest and least force or stress inside of the object. In order to do that, I'm just going to click Create Solution. You've got a number of solutions you can run, from thermodynamics to fluid behavior, how it oscillates, or a number of things. The thing we're interested in is structural behavior. That's going to tell us about the stresses. So make sure you select that. You can also drop this down and pick a couple of materials that are kind of default settings. Just pick the one that's closest to what we're working with, which is probably structural steel. We're going to have to change its material properties later on. Go ahead and create that solution. You may not see a whole lot happen. The solution actually isn't running right now, so make sure that you experiment with pressing play or pause to see some changes. Again, even pressing play, it's just giving me one solid color there. Normally the colors correspond to changes in stress, but I see just one solid color. The reason for that is we didn't define our boundary conditions. It doesn't know what force is being applied to it and where, and what part of the structure is actually being held in space. So those are two things we absolutely have to define to have this be useful at all. Let's first tell it these mounting plates are fixed in space. So I'm going to click one of these faces. You get a little contextual menu that pops up. On the left-hand options here, I see the top option here is a new fixed support. So I'm going to go ahead and click that. Notice it added a little symbol to the middle of that face. That right there means that that is now being held in one position. The next thing is I'm going to select the other bracket and hold that one in space. So clicking this face right in the middle and then putting that as a fixed support. Lastly, we had to define where the force is going to be applied. One of the things that can get us in trouble is if I try to click just the point out here where I want that force to be applied and then tell it to put a new force there, it'll put it in the middle of the face. That's not where I want it. I want it all the way out here, 40 centimeters from the wall. So I'm going to hit escape to undo that. What we actually need to do in order for the force to be out here is to define like a little closed box. So we can do that easily in the sketch menu up here. I'm going to sketch a tiny rectangle on there as the point where the force will actually push down. So hovering my mouse over sketch, I can see it's got a number of shapes that are commonly used. Let's pick the rectangle one. If you're ever unsure what something is, just pause over it for a minute and it'll start to tell you what it is, a rectangle. Just like in other design programs like Fusion360, the first click you make is to select the plane that you're working on. So I'm going to make sure that I'm clicking right on the top face here. If you want to make sure it's a straight down view, which is sometimes easier, you can use the rightmost button here, which is your plane view. All right, let me center that up a little bit. And I'm going to zoom in slightly so it's easier to see this area. So I'm already in the active tool, which is a rectangle. Let me just put a kind of closed rectangle shape out here near the end. I'll hit enter once I release the mouse, just to make sure that that change has been committed. Great, now I've got this closed box. If I go out of this sketching view, I have to click this little 3D model to end the sketch. That now means there's a new closed face right there at the end of the bar. When I go back to my options here to try to select that, well, first of all, you notice it still has an active tool here, which is the pull tool, much like the extrude tool. I don't want that right now. I just want a select tool. So I click on that face. I can now put a new force right in that box. I believe, if you remember from our request from the client, they wanted to make sure this could support at least 186 newtons, which is similar to a 5-gallon bucket full of water. Since the default units were already in newtons, I don't need to include the capital N. If you do anyways, it's going to be okay. I hit enter to commit that change, and now we've got all of the default things that we need in order for the solution to give us something logical. The fixed faces and the force. I'm going to run the simulation again. I turned it off just so it wasn't trying to recalculate as I was making changes to the geometry. So I'm going to press play. And now we actually get a beautiful rainbow as a result. The red are the places where we have the most stress in our design. The blue is where we have the least stress. So it looks like the mounting plates themselves only have a little bit of stress inside the exact center. This whole back bar looks like it's not doing much, so that would be someplace to maybe focus for design modifications if I want to minimize material use. And I see that right there, there's a whole lot of red right at this area. So if I'm trying to make this stronger, maybe I focus on something about this area. Couple other things about the solution here. You can see deflection by turning on this little animation. It changes the what the colors actually represent. Red is areas that have the most deflection from their original position. The units here are millimeters, and this is 2 × 10⁻² millimeters. So that's pretty small, hardly noticeable. Our design constraints from the client said it had to be less than 2 centimeters, so we're well within that. This is extremely exaggerated just so that we can see the amount of motion. Let's turn that off. The other things you may want to experiment with is changing some of the values after you've done this simulation. So if I wanted to adjust the force here, it's easiest to do that over here in this little box. I would just click on this number and I could change that to maybe 200 if I wanted to see how that changed the forces or stresses. Put that back at 186. And another thing that you're going to have to change is the material properties. Right now, structural steel, we're not totally sure if that's the same as the rebar that we're using. We measured ourselves the density and the elastic modulus or Young's modulus of our material. We want to put those values into the simulation so that these stress values are as accurate as possible. You do that by going over to the name structural steel and right-clicking on it. Don't left-click. And then you get this option to open the material library. In there, at the very bottom, it says in the solution we're using structural steel, so click on that. And there you see all of the material properties that are important for these simulations and their values. The ones that matter for structural analysis include density and the elastic modulus or Young's modulus. They both look pretty close to the values you probably found in lab, but I know that density is going to be a little bit less than this value, 7,850. Most groups found a value smaller than that, as well as the elastic modulus. This is 2 × 10⁻11, or 200 billion pascals. Most groups found a value closer to 1.9 × 10⁻11, or 1.8. When you enter your number, it will want you to use kind of the non-standard form of scientific notation. So you're probably either just changing the exponent value, on that scientific notation or the integers in front of it. If you make changes here, be sure to save them by clicking apply. I haven't made any changes, so I'm just going to close that. One last thing, changing the interpreting these numbers. Notice this is in megapascals of stress, so the yield strength of steel is much higher than that, somewhere in the 200, 250, or even 350 megapascals, meaning that we are well within our factor of safety, most likely. Let me try a design change real quick to see if I can use less material. I'm going to show you how to do that by taking out this part of the bracket. Just to test what that does. So easy way to do that is to go to your sketch tool, and I'm going to use the line so that I can kind of enclose that whole space. Again, I have to select what plane I'm drawing on, so I'm going to click right in this face. Now that it's defined that sketch plane, sometimes it's easier to make sure we're looking straight down at it. The line tool, I'm going to begin maybe just in this corner, and I'm going to try to like outline this entire bar. So from that corner, I'm going to go straight down. I'm going to follow up along this edge to there. It gives me a nice guideline, so I know I'm right at the bottom. I'm going to go over to this corner, and then one more line closes up that shape. As soon as it's an enclosed shape, it stops the line drawing tool, so I know that's done. I'm going to stop sketching, go to this 3D view, and use another tool which is already selected for me, the pull tool. If it hadn't made that the active tool, I could go to edit and over to pull and then click. If I select this new enclosed face that I made, I can actually just push it all the way back so that it disappears. I'm going to do it from the side so you can see it. Clicking on this arrow, if I start to go down, it is going to make that thinner and thinner and thinner until I get all the way below, and then it's completely disappeared. So I've essentially removed that bar from the design. The simulation, I had it running the entire time, so it's been updating these values as I did that, and you can see that it has drastically changed the expected stresses within our design. It's still in units of megapascals, but now it's 452. And previously I mentioned that the yield strength of steel, where it starts to plastically deform and get permanently damaged, is somewhere probably in the range of 200 to 350. So this is actually above the yield strength, and I can see right there is a major place that's happening, and on the top as well. So if this is going to snap, break, or deform, it's probably going to be in one of these areas of high stress. I would probably not want to keep that design change I just made, and you can always Control Z to go backwards in time and undo any of your changes that you may have made previously. Hopefully that's enough to get you started on understanding your solution results and making some of the geometry changes in here versus going back to Fusion 360.